Hello, everyone. Welcome. Thank you for joining us. Welcome to another virtual science camp. Feel free to say hi and introduce yourself in the chat. Maybe say where you're from if you're interested in that.
Hello. Hello. Just sit.
Or just yell hello if you prefer. It's good to see everyone here. I'm really excited for today's session. We've got Dave Fish joining us from the Perimeters Institute in Canada, in Waterloo, Ontario. And I grew up about 120 kilometers from Waterloo, so it's great to have another Canadian on. But especially the Perimeter Institute is probably the best place in the world for like really good physics teaching resources. And a bunch of you know and have seen Jeff Wiener from the sessions he was hosting. When I met Jeff at CERN, his message before leaving all the teachers there is, if you go somewhere else for an awesome workshop, then the best place in the world to go is the Perimeter Institute. Dave, who's leading the session today, he's a teacher in residence. He's been a teacher in residence on and off for a long time. He'll be able to tell more detail than I will about that, but I think about a decade or so. And he's developed a lot of the resources. He'll be giving you links to a number of the activities they share. They have tons more stuff. So especially for any of you who are teachers joining, I really recommend you check out Perimeter stuff. There will be a sample of some of the best ones for thinking like a physicist. And yeah, I'm really excited to see what Dave's going to share. So thanks again for joining us, Dave, and I'll turn things over to you.
Thanks, Michael. I'm super excited to be here. It's weird that we can do this where I can be in Canada and you can be in Paris, and we can have a workshop together. That's one of the good things that's going on these days. All right, so I'm going to.
One of the few positive points of the pandemic, right? People think
exactly.
Of doing things like this.
Exactly. So what we're going to do is usually our workshops are really hands-on and we play with a lot of stuff. So what we've tried to do is modify as many things as we can to put online. So I sent you some stuff that you gave to kids that have hopefully they cut them out and they've got them ready to go so that they can do some hands-on stuff. If they don't, I've got online versions for them. So I'm going to throw up my PowerPoint. Hopefully I can do this right, because usually I do it wrong. Hopefully I'm sharing the correct screen with you. That's great.
Yeah, it looks great on my end, yeah.
All right, so I did a workshop a week ago or 2 weeks ago, and somehow I lost, it still worked fine, but on my end, I couldn't see anything. Okay, so this is the Perimeter Institute here. It's a beautiful building. I wish I could be in it right now, but under COVID regulations, I haven't been able to be in my office since I came back to work for Perimeter. I miss it. It's a great place to be. It's about 20 years old, and it's one of the world's leading theoretical physics institutes. So in this building, you have people who are trying to answer fundamental questions about the universe. They aren't doing experiments. A lot of them have colleagues who do experiments, but they don't do experiments. They are the ones who sit on whiteboards and blackboards and computers and make models and make predictions. And it's a super exciting place to be. It's in Toronto, it's in Waterloo, which is near Toronto, just to give people a chance to understand where I'm coming from. We're in what's called Southwestern Ontario. And what do the people at Perimeter study? Well, they study things like gravity and cosmology and particle physics and quantum mechanics. And they're asking fundamental questions, like things like, what is space? What is time? What is matter? And it's actually really interesting. A lot of the things that you might think are silly questions to ask is what these people are spending their entire lives asking. Things like, what is mass? Or what is charge? What is time? They will actually spend their entire lives trying to understand the nature of time. And it's a really interesting, special place to be. Now, what we want to talk about today is what makes scientists different. How is it that scientists think? And we have sometimes got the wrong idea. Sometimes we think scientists are people who are almost like robots, where they follow a very strict rules of how things work. And that's not true. Scientists are creative. They're curious. I often look at these scientists that I work with. They're just big kids. They're those curious kids, and they've managed to find a way to stay curious and to make a living being just curious. And so that's what we're going to do today. We're going to play around today with being curious. And we're going to try to look at a couple of little mysteries and see how scientific thinking helps us solve these mysteries, or helps us approach these mysteries. Not even solve them, but just how to sometimes put some framing around them so that they make sense. So the very first thing about scientists is we need to know that scientists are curious. And for scientists to be curious, that means that they ask a lot of questions. So I have here a little something. And if you're a scientist, and I see some faces peering in, these are people who are curious. And so you look at something like this and you're like, well, that's not very special. And you wonder, well, what makes things happen? And scientists are people who look at things and say, well, how does that work? And I really miss the fact that I am not in a room with you right now. Because every time I do this activity, and I have a room full of kids or a room full of adults, at this point, it goes deathly quiet. And everybody settles down and starts to try to figure out what's going on. And that's what we're going to do right now. I want everybody to look very carefully, make really good observations about what I'm doing. And I want you to feel, first of all, before you even try to solve what's going on here, I want you to feel that thing that's going on inside your head and inside your heart as you try to figure out what's going on here. This is science. Science is trying to figure out mysteries. So what I want you to do right now, if you have a paper and a pencil, I want you to try to draw a picture of what's going on inside this tube. Okay? How are these strings connected? So take a minute and try to figure this out. Now I'm going to take all the pressure off of you. There is no one right answer. Okay? In my classroom, I have 4 of these, and each one is different inside. So there's no pressure that you're going to have to get the right answer. But I want you to come up with something. I want you to try to come up with an answer for how these strings are all connected. So I'm going to give you about 2 minutes, and then I'm going to ask you to share something that you can give a solution for it. And what you're doing right now is you are building a model. That's the fancy language in science. You are going to build a model for how you think these ropes are connected.
And there were already a couple of good guesses in the chat from Alex, so hopefully, or maybe that'll figure into the diagram what you think might be happening.
All right. It has something on the back. You are changing hands, but always with a thumb at the back. Oh, you think I'm trying to trick you? Alex, who hurt you? No, there's no trick. There is no trick.
But that could be part of a model to explain it, and
Yeah,
that
it could be
one of the correct answers. Like now you might have an idea for a fifth one you could do.
I have lots of different options. I've been doing this for years, and you guys keep coming up with really cool options, and I'm like, yeah, I could do that. So I actually have more equipment out in my my workshop area. I might this summer build a few more and see if I can make some really fancy ones.
Well, I'm guessing some of your new ideas have come from participants having ideas that explain it.
Oh,
and
yeah.
Those are things that could be right answers, and you just hadn't made that into the right answer yet.
Yeah, absolutely. Yeah, there's one in particular that's shown up a few times, and it's just really tricky to build. So I haven't built it. It involves pulleys, and I haven't done it. So there's a clue for you. These ones don't have pulleys in them, but there is a design that you can use pulleys, and I'm dying to try it, but I think it's beyond my skill level. I'm not a great craftsman.
That sounds like that would be tricky to machine to get it so they're not just clunking around. Like, I guess they'd need to be in a fair bit of tension, but
yeah, I'd have to figure out some way to mount them. So I don't know. That's the trick. I have a design on paper somewhere.
I think I've got it.
So let's see, what guesses do we have? Maybe the strings are twisted inside and somehow linked inside. Yeah, that's true. Anybody? Oh, okay. Alex has a picture. Oh, very nice, Alex. So he says they're linked by some kind of circle.
Like a ring in the middle.
A ring in the middle. Okay, so Alex says there's a ring in the middle. Each string connects two strings. How are they connected, Ace? They're tied together. Okay, so there's some knots inside here. Okay, that's possible.
And if anyone else feels like sharing a diagram they made, please feel free to turn on your camera and share your diagram as well.
And don't be afraid to take chances. It's funny, when I do this with teachers, they're really scared. Oh, that's a good one, John. Yeah, the strings can just be twisted together like that. Very good. So Alex, we have Alex saying that there might be a ring in there. And we have John saying that the strings are just connected, there's no ring. They're just directly twisted around each other. So both of those models work. Both of those models give us the observations that we need. And that's really important because in science, that's what it's all about. In science, it's all about building a model that can explain what we measure, what we see. Now, the other thing that we do in science is we take competing models and we say, okay, how can I tell the difference between, I guess it's now Gabrielle and Alex? How can we tell the difference? What can I do? What experiment could I do that would allow me to challenge one of the models, to show that one model is better than the other? Any ideas?
We could test out the strings. Like, for example, on mine, if you pulled two at the bottom, then logically the two top ones should both go down.
Yeah.
It wouldn't exactly do the same thing on hers.
Okay, you're right. Because Gabrielle's, she has it twisted vertically.
Yeah.
So there would be a difference. Now, if she had it twisted horizontally, so that the top one wove into the bottom one instead of the left and the right. Okay, then we wouldn't be able to tell the difference between yours, Alex, unless we did a different experiment. How's this for a different experiment? What if I do this? Oh, there's something inside this tube that's rattling around. So whose model does that support?
More like mine with something inside it, yeah.
Yeah, it gives a better, it supports. Now this is really important. In science, we're always careful to not say, oh, Alex must be right then. What we would say is the new data supports your model and it refutes her model. That's kind of the language we use, because we're never quite sure who's right and who's wrong. Okay? But yeah, you've now developed a really good model. And you know what's really cool? Are you guys locked down out of school? Michael, are they out of school now?
No, we're still in school for now.
You still get to go to school. Okay. Because this is cool. If you really want to, if you want to torture your parents, you can build one of these yourselves.
Yeah, it won't be that hard.
Okay. Take the inside like of a toilet roll. You can just use or paper towel roll.
Yeah.
Poke a couple of holes in it, run some strings through, do however you want to do the connection, and then seal up the top and the bottom, and then give it to your mom or dad to say, okay, figure it out.
Yeah.
Okay? And they're not allowed to look inside, what's really important. They're not allowed to look inside to see how you did it.
Can you take the top of that one to see how it works?
No. Because the way nature works, we are never allowed to know. You see, you can spend your entire life as a scientist working on, Gabrielle's already going to work on it. There we go. She's not taking, not slowing down.
That's great.
Now, the thing is, we can never actually know what's going on inside here. Alex, the ones I have in my classroom, I've glued shut.
Great.
You cannot possibly get them open. These ones, this one actually you can open it. But the ones I have in my classroom, because I leave it with students when my back is turned, you know how you guys would do it, right? You would all rip the top off. So I glued them shut.
Well, you can also use a powerful magnet to know if there's something in it. Like if you attached a magnet to the side and put it on the bottom, and then you'd know if there's something metal like a ring holding it together inside.
Precisely. And this is what science does, right, Alex? Is we ramp up the tests and we say, okay, what other tests could I do? Oh, I could x-ray it. I could put it into an MRI machine. I could, what other ways could I do this, right? I could, you know, there's all sorts of different things I could do to try to see what's going on inside here. But ultimately, we can never know for sure. Okay? And so what we can do is we can narrow down that window that says, what are the possibilities? And when we get to a situation where that window is really, really, really small, we start to say, yeah, we're pretty sure this is what it is. Okay? But in science, we can't actually ever know for sure. We have a nice picture of the atom. Like we're going to talk about some particle physics in a minute. Well, there is a fundamental limit in science that says I can't actually see what's going on inside an atom. Never. I can never look inside the black box of an atom. The best I can do is see the surface of an atom. If I try to get inside, I run into some problems with physics, and it doesn't let me know what's going on. And so this is a really fundamental thing. If you want to look with a microscope at something, there is a fundamental limit to how small you can see something based on the wavelength of light. Okay? You can't see past about the size of a big bacteria, basically. You would not be able to see the COVID virus with an optical microscope. Too small. Okay? So we build models, we test our models. That's a really important thing. in science.
Yeah.
Now, we're going to make another model. We're going to look at this. Now, hopefully you all you've made a little paper cube. So hopefully you've got something that looks like this. It's got a little paper cube. If not, it's okay, because we're going to do something online. When I do these in my workshops, we use a wooden cube. They travel a little bit better than the paper one. Now, what we're going to do is we're going to take a look at, hopefully I can pull this up, share that screen. Okay, now are you guys seeing this picture of a cube on your screen now? Did I share the right screen?
Well, yeah.
Perfect,
Yeah.
okay. So if you didn't make a paper version, you can take a look at this one. Now, it's really important in science that we take our time and build up a model, that we don't jump to the answer. How many times have you had a teacher tell you to explain your thinking or show your work? They don't want you to just jump to the end. Really important. We have 3 steps to what we want to do. First step, we want to make some observations. Second step, we want to make some inferences. And so what an inference is how are your observations connected? And then the third thing is we want to then build a model based on your inferences. So the first thing I want us to do, I want you to take a look at your cube, either the paper one that you've got or this one online. And I want you to list out some observations. Okay? Don't try to guess what they mean. Start with just the observations. What do you see? Okay? And then I want you can just put some observations into the chat as you make them. So what I'm going to do is I'm just going to move the cube around so that you can see. My colleague made this. I have no idea how he did it. It's really cool. Oh, I want to make sure. If you have a paper version, look at your square that says key on. Does it have a 2 in the bottom left corner? It should have a 2. My early version of this had a 4 there as a typo. So make sure it says 2 in that corner. Okay.
And Gabrielle's confirmed yes.
Excellent. Thank you, Gabrielle. All right. So now, in the chat, I want you to write down an observation that you are making.
And Dave, do you want me to read the observations from the chat or just leave things for a minute?
We can just leave things for a minute and let them build. I have no idea where the chat. Yeah, you're going to have to at some point, because for some reason the chat has disappeared from me.
Yeah, often when you're sharing a screen, it kind of covers everything else, and it's hard to find the chat. But don't worry, we've got 2 observations in the chat. Hopefully, there are going to be a couple more coming through.
And you know what? Sometimes one of the things I've been doing lately is I've been listening to Sherlock Holmes stories. And one of the things that Sherlock Holmes says is never sort of ignore an obvious observation. Like sometimes when he's trying to collect clues for a crime, people are like, well, that won't matter. He's like, no, you can't decide what matters until the end. And so he's like, I need to know all the details. Like the story I listened to this morning, he asked, what newspaper was the guy reading? And people are like, who cares what newspaper he's reading? But to him, it was really important which newspaper. So even as you look at this, how many sides are on a cube? Right? Did anybody observe that there are six sides?
Mm.
Oh, and look, there's one blank side. Was that an observation that people made?
Yeah, that didn't come through yet.
Okay, so now we notice, what else do we see? What do we observe on any one face?
There's a word and two numbers.
Okay, there's words and two numbers. What do you notice about the words?
The word are
The
spelled.
word,
Go on.
well, the biggest number of the two numbers on the page is the number of letters that make up the word.
Oh, okay, now you got to be careful. You're jumping
Except
ahead,
on
and
the-
I'm not
except on-
surprised, Gabrielle, because you seem to be fast. But you're jumping ahead and you're trying to connect different observations. That's our next step. And it's always frustrating to do this. That's why I'm making everybody slow down and just say, okay, what are your observations? So you guys are right. Your observations, you see numbers, you see names. You see 6 sides, but one side is blank. Okay, now let's look for, yep.
Oh, I was just going to say we have some people who added that there's 2 numbers per face.
Yeah.
And there's more than 1 number on each face. Yeah, so those were additional observations that came through in the chat.
Excellent. Okay, so now let's try to make some connections between our observations. So I want you to take a look at the cubes and say, okay, what are the connections? So Gabrielle gave us one already, that there's maybe a connection between one of the numbers and the words.
Well, for now, what I've seen, yeah, it's always the top right, which is also the biggest number, which is the number of letters in the word.
I think example
Okay.
in work it is a second, and 4 it is a number of letters.
Yeah, so we see that on each face, the number in the top right corner matches the number of letters in the name. Okay, great. Can we see a connection with the other number?
I'm going to guess something about which side it's on. For example, the face.
Okay, so then what I want you to do, Alex, I want you to look carefully and say, all right, so you would say that this is number 2 face.
Yeah.
And this one, well, sorry, I don't know how it spins. There's a number 3 face here.
But there's another number 3, isn't there? I've seen that before.
Oh, there's another number 3. Okay, so you have to take your inference and kind of step back and say, okay, I need a different answer. Okay, this is good though. Keep throwing out your ideas. Somebody might build on your idea and say, does anybody notice something else about the names? You see a pattern that maybe is there with the name.
If there's a 3 on the side, then it has an S in the name.
Okay, so on this side, you see there's a 3 and an S.
And if there's a 2, then it's a K.
A 2 has a K, okay.
And
that could work.
Like names with same starting letter are at the opposite sides of each other.
Oh, very good. Look at this. K is on one side, and on the opposite side is another K. That's cool. And on this side, you've got an S, and over here you have an S. Great. That's fantastic. So let's look on the side here. Oh, this guy's on his own. So he's not going to teach us anything right now, because opposite of Frank is a blank. I have no idea how to get to that blank. There it goes. All right. So we have a model that we're building. Does everybody feel that? Do you feel how you've got a model that's forming in your head? This is how scientists work. We gather observations. The more observations we have, the better. Then we start to try to connect one observation to another. and we start to build a story, or what we would also call a model. Now, ultimately, what we want to do with that model is build a prediction and to say, where are we going to go with that? How is that going to help us? So let's see if we can build a model for what's going to go on this blank face. So I have a blank. So I'm going to look. We've already said that the opposite sides have some clues to us. So I want you to think right now, what could go on that blank face? What will be the numbers? What will be the name? I want everybody to spend about a minute or two right now just thinking on their own. You create your own model. There is, again, there is no right answer here. There are different answers. There are better answers, but there's no one right answer. Wouldn't you like this in school if this is the way it always was? Never always have to be the right answer, just good enough, as long as you can explain it. Oh, we have somebody raising their hand. Ladislav?
Yeah, I just, can I say what I think?
Sure, go ahead.
Okay, so I think on the blank side, there will be a name starting with an F because it's an opposite side. It means that there will be a 4 on left down side.
Yeah.
And I noticed that the bigger number is going like 3 on Sam, 4 on Cohen, 5 on Frank, 6 on Keisha, and 7 on Samina. So I think it might be 8 or 2. Probably 8.
Excellent. So you have to find a name that starts with F and is 8 letters long. Okay. Anybody else have a different idea?
Could you turn it round a bit more, please?
Sure.
Okay.
I guess Dave doesn't see the chat, as he said. Someone asked if you would mind to share this with teachers. Share this.
Yeah,
anyway.
oh yeah, I was going to put that in the chat, wasn't I? Except I can't find the chat now. Yes, I'll share this link. I'm going to for teachers. I'm going to give Michael a document that's got all the links to the things I'm going to share, including to the resources where these things come from. They're everything for the teachers in the crowd and for you guys. Anything that Perimeter does is free. It's all, you can go to our website and download anything you want. And most of pretty well everything we have has also been translated into French and Spanish and Portuguese now. So we're slowly becoming an international resource for educational materials. So it's all free. I will give Michael some links to these things. Again, this is just something we created for our online world. As all the teachers in the crowd know, we've been scrambling to do things online. And so we've tried to build some of our resources online. Okay, so anybody else have a guess? So we have that the blank should have a 4 in the bottom left corner. It should be a name that starts with F. And up in the right corner, maybe an 8.
I also noticed that there's usually like a male sounding name and a female sounding name.
Very nice.
So it would
Yes.
probably be like a female sounding name like Francesca or something.
Very nice. So there you go. We kind of went with boy girl names, but not necessarily. Like Sam is fairly ambiguous. I know Sam's, I've taught male Sams and female Sams. But yeah, that is one thing that you could infer from your observations, is on one side you seem to have a girl's name and on the other side you seem to have a boy's name. So you have Keon and you have Keisha and Sam and Samina. So Frank would be matched with Francesca. Sure. Ladislav?
So I was just gonna.
Also.
Okay. Yes. Go ahead.
Opposition Keon, Keisha. There are not one first. There are two first letters the same. Sam and Samina. There are two first letters the same. Not one. There are two.
Not even two. Keep going. How many of the letters match?
I think there are. I think there are 5 letters. 5 letters in blank face. I think there are 5 letters.
And
right. Okay. Sorry.
And there was a guess quite along those lines from, or an observation quite along those lines from Yester about the bottom left numbers, which is the number of letters in common between the names.
Yeah.
So Yester's saying then it should be 4 and the top right should be 8.
Okay. And so, and then that also then, Yester, you would be what we would say is you're putting a constraint on something. So the name wouldn't just have to start with F. You're saying that this number down here, the 4, says how many letters in common.
Yes, Dave, so, that's what I'm saying. Yeah.
Yeah. So you're putting a constraint on this that says, okay, the name over here doesn't just start with F. It has to start with F-R-A-N.
A-N. Exactly. Yeah.
Yeah. So you could have a Francine, Francis, Francesca.
Francesca. Yeah. Any of those names.
Yeah. That's great. So the neat thing here is what we're doing is building up a model. And then you see how we can make predictions with that model. Now, in this case, I don't have an answer for you to check. Okay, there is no answer to this activity. There are just options. And if you can build a model that is consistent with the observations, then we have to entertain that model. We have to say, okay, that model could work. Okay, and that model predicts this. Now,
and it looks like Ladislav wanted to say something as well.
Yeah, I said the theory that there will be 8 letters at the blank side, but now I noticed something different. Like in the names that start with S, there are 3 and 7 letters. When the name starts with K, there is 4 and 6, and maybe when it starts with F, there will be 5 and 5. Like it will always be 10. Maybe.
Oh, see, it just so happens that when we designed this activity, we built in all sorts of patterns that you can play with. Now, it turns out that nature sometimes has patterns in it, and sometimes those patterns mean things, and sometimes they don't. And that's the beauty of what we're going to do. So now what we're going to do, this activity has just been about building up so what we've been doing is just building up a model about this cube. Now, the cube doesn't mean anything, right? This cube is just something we created for practice. Now what we're going to do is some real physics. Alex, you have a question?
I did something really complicated, but basically I multiplied both numbers on each corners, and then I think I put the ones, like the smaller one, on the matching face, like divided by the matching face. And at the end, when you compare them all, you get 12 28, 16 28, 19 28. And I don't know if that has anything to do with it. But when you multiply that by 2, so basically make it all proportional, then each leap is 4 more.
Nice. Yeah. So the thing is, Alex, you've got the makings of a theoretical physicist because you like to play around looking for patterns. And this is exactly what physicists do. The theoretical physicists are constantly trying to find what is the pattern behind something. Now, sometimes those patterns mean things. Sometimes they don't. Okay. Now, what we're going to do is we're going to take this idea and we are actually going to do some physics now. We're going to do some particle physics. So Michael sent out a piece of paper for you that has a bunch of little squares on it that hopefully you cut up and you made yourselves little cards. I do not have a physical version of this. Now, we are going to do some particle physics. Now, when you do particle physics, there are certain things that we use to describe particles. We have this thing called spin. Basically, it has to do with how does this thing behave under a magnetic field? That's partly it. It's a little complicated, but it's there. It's just spin. It's electric charge. So some things feel electricity, some things don't. There's this thing called strangeness. And you might go, oh, that's weird. What is that? It actually comes from the first time it was observed, the physicists actually said, well, that's strange. And it stuck. The particles that have this thing were called strange particles because they behaved weird. And so we actually created this property called strangeness. Then there's the mass, and then on the card is also a date. Now, this is very similar. I'm going to give you an activity that's very similar to what we've just done. Okay, we're going to look for patterns. Now, what I want you to do, you have 9 cards. Now, let me see if I can find the chat now. Yes, I can find the chat now. Now, can I find my Word document? Okay. Found it. Okay. I'm going to, for those of you who don't have the paper version, I've just given you a link in the chat to a Google Doc that you can make a copy of it for yourself. And it's just a Google slide that's got these pictures on it, but you'll be able to drag them around and manipulate them. So now what you have are 9 cards. I want you to look at them carefully and say, okay, what information do I have? And how can I organize these cards? So how can I arrange them? This is a really important part of trying to do science, is not just getting all these observations and data, but then how do you organize them so that you can see patterns? When I was a kid, I had what are called hockey cards. Michael probably had them too. And it was for all our sports teams. Maybe in France, you got soccer cards, I don't know, or football cards. And so what you would have is you would have on it would say what position the player played and what team they're on, and certain things, how many goals they scored last year. And you could arrange your cards. You could have a pile that were all your defensemen and all your forwards and all your goalies, or you could have a pile that were all the Toronto Maple Leafs. And you could organize those cards however you wanted. So what I want you to do is take these cards and I want you to try to organize them. And you're going to organize them in such a way that you can see that one card is missing. That's the question mark. So once you find your pattern should show that one card is missing. And you, if you have a good pattern, should be able to tell me what the spin of that particle is, what the charge of that particle is, what the strangeness of that particle is, what the mass of that particle will be, approximately. And you could probably even guess when it was discovered. Okay? So I want you to try this. Take a few minutes. It's really easy with the physical cards. If you can cut out the physical cards and just rearrange them, it's easy to manipulate. On the Google Doc, you can just slide it around, the squares around. So give it a try. Okay, once
Can I try an answer?
Sorry, Alex?
Can I try an answer?
Sure. What I was just going to say, if you want to enter into the chat your guesses, that would be great. And that way people can keep concentrating. If they don't want to read the chat, they don't have to see what your guess is.
Sorry, I didn't realize that when you pressed enter, it was sent.
No, that's fine. That's fine.
Let's try.
And for the teachers in the crowd, I've put up a link for the 3D animation.
I don't find answer, but I find that when s minus 2, then discovered 1962, but when s minus 1, discovered 1960 when S0 then discovered 1954.
Yeah, so you've noticed the pattern there. You've noticed part of the pattern is that the first particles to be discovered were the ones that had no strangeness. And then they discovered, okay, the particles that had a little bit of strangeness. And then they discovered another group of particles that had more strangeness. Excellent. So Alex says you got Q plus 1, S minus 1 discovered in 1960.
Yeah.
But I think you already have that one, Alex.
We do.
I think so. I've got one on my screen.
Then I didn't copy it down. Oh yeah. Then sorry.
That's fine.
I got my papers muddled up then.
Yeah.
But that's a really good sign. If you were missing that card in your stack, you're able to predict it. So it shows you got a really good pattern that you were following.
Yeah, exactly. Exactly.
Oh, yeah, okay, sorry. Can it be plus 2 minus 1 discovered in 1960?
Plus 2 minus 1. It could be, but no. Now, here's where it's different, Alex. This is the challenge of science, is that ultimately, even though like with the black box and with the cubes, any answer could happen. In science, your model actually has to match nature.
So then the last
when we do experiments, nature is going to tell us whether or not that particle actually exists.
Oh, wait, okay, I've got it. We have to go upwards from 0, minus 1, minus 2. So the one missing is plus 1, minus 2, discovered in 1960, sorry, wait a second, 1954, I think it was. No, trying to look for the thing. Oops. Where did I put it? Oh yeah, okay, so it's plus 1, minus 2, discovered in 1962.
Let's take a look. Let's see. So I've got here, you're about to see some masterful PowerPoint animations here. Okay. So I've got my cards laid out. And what I'm going to do is I'm going to arrange them into rows and columns. Okay. So in the first row, I'm putting the S equals 0. In the second row, I put the S equals minus 1. In the third row, I put S equals minus 2. And then I noticed also, look at my columns.
Oh, yeah.
The columns are the right-hand column is Q equals minus 1. Then I've got Q equals 0. Then I've got Q equals plus 1 and Q equals plus 2. Now, the interesting thing is when I do this workshop with teachers and we tell them the card is missing, they want to build a rectangle so badly. Like they think that nature wants everything to have the same number of rows and columns. And it turns out that the pattern that we actually want here is a triangle. So with this picture on your board,
Oh, okay.
can you
We,
now tell me what that particle is going to look like? So
yes, but we can't say the year.
But no, but take a look. The first group was 1954.
Yep.
Then it was
Oh,
1960. Then it was 1962.
So we know it's going to be later than 1962.
Exactly, Alex. Okay, and then think about the mass. Look at the mass. On the bottom, your mass is about 1230. Then it
Yeah.
goes to 1380.
And
Then it goes to 1530.
So we know it's going to be around 17.
I think S minus 3 and discovered 1962.
That's a great guess. Let's take a look. Let's see what we can put together. So we have all the strangeness in one row, all the same charge in the same column. You've got increasing mass. This is what we mean when we say we look for patterns. Sometimes in order to see a pattern, you have to organize your data. And that's what particle physicists are great at, is organizing data. So let's look. Spin of 3 halves. Well, all these particles had spin of 3 halves. The electric charge, it's in the right-hand column. So we would say the electric charge is -1. It's in the top row, which according to our pattern is 0, -1, -2, -3. Mass will be somewhere around 1680. And it was discovered in 1964. This is what's called the omega minus particle. And guess what? If you had been around in 1960 and made this prediction, you'd get the Nobel Prize.
Oh.
Murray Gell-Mann won the Nobel Prize for predicting this very particle. Now, he did a lot of other things too. But the cool thing is, see, what happened was he went to a conference. And in that conference, the researchers from CERN announced the existence of the S equals -2 particles from the 1960 discovery or 62 discovery. And they were reporting on these things. And he put his hand up at the end of the conference. At the end of these presentations, they always, it's interesting. The typical thing in sort of old school was that when you ask questions at the end of your presentation, you always go to the senior person in the room first if they have a comment. And Murray Gell-Mann was considered sort of the senior person. He put his hand up and he said, based on what you predict, what you've just announced, I predict the existence of a particle. And he described exactly this. And people went out and discovered and found it. Okay. Now, the interesting thing at Perimeter, when we have a talk, the very first questions, the first thing we always do is we say, do any of the students have questions? We deliberately turn that on its head and we let the young people ask their questions first instead of going to the old people first. It's just kind of a weird thing that we do. But anyways, Murray Gell-Mann predicted the existence of the omega minus particle based on essentially what you just did now. So think about that. You just won a Nobel Prize. When your parents ask you in a few minutes, they say, what'd you do? You could say, I won a Nobel Prize. Okay. Michael?
And there was an interesting comment. Ladislav was saying the mass doesn't have to be greater than 1600. Do you have any thoughts on that, Dave? Or Ladislav, do you want to explain why?
Well, no, I just wanted to say that, of course, it's logical that it is greater than 1600, but we only knew that it will be higher than 1535, like when we built that triangle.
Yeah, but if you notice in the triangle, the difference in mass from one row to the next is about 150 mega electron volts. So when you go up each row, you go up. The mass goes up by
I
about.
can't understand how we can find the mass there.
How we
Mass.
measure that mass? So basically the way we measure mass in particle physics is we measure the energy of the particle. And that has to do with, and then we can look at, there's various ways of doing this. You can say, okay, how does this particle behave in a magnetic field? And we can then infer its momentum. And from its momentum, we can then infer its mass. Or we can take a look at the energy in the particle and we can work backwards and find its mass. It depends on the nature of the particle and the experiment we're doing. There are different ways to do this. It's a really challenging thing. You can't just go to the bathroom scale and put an omega minus on the scale and say, how heavy are you? You probably don't notice this, but even that unit for mass, that's called a mega electron volt. So it's actually a measurement of energy that's in there. I think a lot of you would know a guy named Albert Einstein. And Einstein, one of the famous things he said was E equals mc squared. And what he showed was that mass is energy. So if I can measure the energy of a particle, I know its mass. And so that's kind of what we're doing. But yeah, it's what we see is each generation, each row that you go up went up by about 150. So just by looking at the pattern, Gell-Mann was able to say, here's roughly what you're looking for. Go find it. And within 2 years, they found it. Alex?
Isn't the mass 16? It should be 1673, shouldn't it?
It actually is 1672. Like that's what the measured mass was.
It says 6. Yeah.
Sorry?
It says 0.5 on Google. So logically,
okay.
It's rounded on to 3.
It all depends on which resource you're looking at. Yeah.
And I had a question.
Yeah.
So I know that the antiparticle is going to have +1 instead. Does it change the mass or not?
No.
Okay.
No, in an antiparticle, it has exactly the same mass, although that is one of the cutting edge experiments that they're doing at CERN. And in the next year, we should hear this. Once CERN gets up and running again with its next observation run, there are a couple of really cool experiments. One's called G-bar, and one's called, I apologize, I forget the other one. And what they're doing, they're trying to say, does the mass of an antiparticle behave the same as the mass of a particle? And in one of the experiments, what they're going to do is take the antiparticle and drop it. And they actually want to see, they don't know if it's going to fall or if it's going to go up.
Oh, yeah.
See, we've never been able to tell that because we've never been able to produce enough antimatter to actually see how it behaves under a gravitational field.
And if, for example, it did go up, wouldn't it go up at the same speed as the other thing went down?
Yeah, but there's a lot of, it's a really difficult experiment to do. So it's not as simple as just dropping a ball, because what you're talking about is dropping a couple of atoms. And so there's, like, when you think about buoyancy effects and all sorts of other things, it's really, really complex, but it's going to be exciting. It's going to be super exciting. Nobody really expects it to behave differently. Like nobody, I don't know if anybody is going to make a bet that the antimatter is going to float away.
You could become a millionaire if you got it right.
But well, yeah, the thing is, we got to check. Like that's the nature of science. Yeah, we're pretty sure it's going to behave like normal mass. But in science, we don't want to be pretty sure. We want to test it. And so that's one of the big experiments going on at CERN, is really taking a look at antimatter and saying, how does it behave? In what ways is it the same as matter? And in what ways is it different than matter?
But if
Okay.
if the antiparticle goes up, wouldn't it have to have more energy than the one going down because gravity would be going against it?
Whoa, yes. Yes, see, Gabriel, that's brilliant. Okay, because yeah, your position in a gravitational field is connected to your energy. So then that would be part of the problem. If that is what happens, oh, that changes our understanding of energy, that changes our understanding of all sorts of things. So this is why we do these experiments, is that we're hoping. See, one thing to remember, to realize about scientists, they actually are, yeah, it's really exciting to do an experiment and have the result come out the way you wanted it. But really, that's not what excites scientists. What scientists hope for is an experiment that is going to break their model. Okay, that's what we live for. We want a challenge. We want something that has to be explained. So that's one of the things. Yeah. So just in this little activity that you did today, you predicted the existence of the omega minus. Now we're kind of getting to the end of our time. So I'm going to just go to the very end here. I'm going to skip over this little thing.
And can I interrupt with a quick addition about antimatter?
Yep.
So those of you who joined for Jeff's talk on accelerators and decelerators, or the virtual tour of the antimatter factory, might remember a similar question was asked to Jeff, and he was explaining the G-bar. And one thing that they do know already is that antiprotons on their own are accelerated downwards due to gravity, because in the decelerator ring, they need to compensate for the particles falling under gravity as they're decelerating. So they know that individual antiparticles are affected by gravity, as you'd predict for regular particles. But what they're checking precisely at the G-bar is that when it's together as an anti-hydrogen atom, that's affected. So they already have some evidence to support that it probably falls down, because if you take the pieces apart, they do, but they've not yet. And that's one of the things they're working on, that the pieces together will fall down. And if anyone ends up with more questions, like precise ones about antimatter you want me to relay to Jeff, I'm always happy to get back in touch with him. And he's always really happy to help answer more questions. And if you want to look at the recording of that session, it'll be published in the near future. So you can check that out as well.
Yeah, and part of what they're also doing with this next generation of experiment is they've seen the antiprotons, they do dip, but they need to make better measurements to see how much is it dipping? Is it dipping the way we expect it to? So that's not, the H-bar is doing one thing. There's 3 different antimatter experiments that are looking at antimatter under gravity. And one of them is basically analyzing the beam as it travels. And there's another one that's actually just going to drop these things. And so it's a really fun experiment, and it's cool. Just want to wrap up here. I just want to, we have a website called perimeterinstitute.ca that's got a resources page. And for the teachers in the crowd, you can go there and look around and download stuff. For the students, there's stuff there as well. You can download posters. We have some really interesting posters that if you wanted to look at. And it's just called resources.perimeterinstitute.ca. It looks like a store. Don't be shy. You probably have to make an account just so you can download to a form. But you're not going to have to pay for anything. It's just that we use Shopify. So Shopify is a software company that makes online stores. So everything looks like a store, but it's all free. So if you go to our resource center, you can get all sorts of fun resources. You can go to our website, the Perimeter Institute website, and look around. all sorts of lectures and classes are online. So if we do public lectures every month. So if you can peruse through our public lectures and say, hey, I really want to learn more about the Event Horizon Telescope, or more about black holes, or more about particle physics, or whatever. Look through and see if there's a talk that appeals to you. And there's my email. Feel free to send me emails if you have questions. I'm always happy to answer questions.
Thank you.
Yeah, this has been great. Thank you again, David. It's been wonderful having you take us through these activities, and to the participants as well. Like, there was a lot of really good participation from a lot of you guys, and it wouldn't have been as good if you guys weren't as enthusiastic and making hypotheses. So it's been really great. Thank you, everyone, for participating, and thank you again, Dave.
Happy to be here, and I expect I'll see some of you in the future. We have summer camps for really bright high school students. We have a master's program. We have PhDs, and Alex's ears perked up.
Yeah.
Yes. Take a look at, it's called ISSYP, the International Summer School for Young Physicists. So
That
probably
sounds
in
great.
your final year of high school is when you would be looking at coming.
Yeah, I've just finishing up college, and then I'll be into high school.
Okay, well, we'll see you in 3 or 4 years.
Yeah, probably.
Hopefully by then we'll be back in real life and it won't be online. This year it's online.
It's online.
Yeah.
And for teachers, they also have wonderful programs that are like the summer camp. In fact, the EinsteinPlus this year is being replaced by the summer teacher summer camp.
Online teacher camp. Yeah, so our online teacher camp this year is a week of basically doing about 2 workshops a day, like this.
So I think we'll wrap up there, but thank you again, and have a great evening, everyone.